Hello, we are the group number 2, and our topic is Federated Learning for Wireless Communications. With the 5G technology, there is an interest to complement the traditional model driven approaches with data driven approaches. But the problem with this is that these traditional machine learning approaches rely on having data and the processing power locally, data which is mostly private and that requires a large communication overhead to be transmitted. A solution for this is federated learning, where you have a federation of distributed learners that performs a local model training with their local data. Uh, in this way, you keep all the private data where it is generated. Then these local parameters are sent to an aggregator unit, which update a global model, and the global parameters are sent back to the local model for their use. In this way, you have a personalized model for each user. They keep their data private, and we avoid sending the raw data. What makes federated learning different from the existing distributed learning schemes is that one of the common assumptions of the existing schemes is that the data samples of the learners are independent and identically distributed. But in federated learning, we have that the learners may be observing separate parts of the process with possible overlaps. So we generate data sets that are not representative of the distribution of the entire data. We also have that the data sets are unbalanced in size. Some users may have larger data sets than others. And in federated learning, the data sets are massively distributed among the local learners. In the existing schemes, uh, the data sample per learner is larger than the total number of learners, but in federated learning, uh, the number of learners is larger than the number of data samples you have per learner. Now, for the application of federated learning for wireless communication, we have edge computing and caching, where the idea is to bring popular content closer to the X terminals, the base stations, so that they can conveniently access to this popular data. But as we said, this is not possible because this is private data from the users. So the idea of federated learning is to utilize the locally trained models rather than directly access the user data. Then we have the spectrum management. So for the 5G verticals, which are focused for the vertical markets, for the 5G verticals to work, we need a hybrid spectrum of low and high frequencies. But the problem with this is that we need the radios to share their spectrum utilization, which may not be possible because uh, they may not be able to share this data because it's private. Also, we require a lot of processing power and large scale optimization. So again, the federated learning approach is to share the local model parameters instead of just sending the raw data. So you can you can save the privacy and also the the requirements of processing and optimization. Then we have the 5G core network, and the network data analytic function is a new network function that provides the ability to make use of intelligent techniques in the network management system. Uh, so you could be able to connect to any network function and utilize any data, and the network should be able to manage itself, requiring no or very few human interaction. But there could be situations where the distributed data sets may share the same sample space but different feature space. Uh, an example of this could be a network where you have two offices, and one office have some data about the users, and then the other office the other office have uh, another data. Uh, so like in figure B, uh, we have that data from A have some features that data from B don't have, and the same for data from B, which have some features that data from A don't have. So the vertical federated learning can address these issues by making each entity in the core network transfers just the local and create model, uh, and just make use of these local parameters to calculate the global parameters.
Research on federated learning is still in its early stages. Despite the apparent opportunities it offers from the edge to the core networks, there exists several critical challenges in applying federated learning to wireless networks. Some of the challenges and future research directions are discussed next. Security and privacy challenge and considerations. Protecting privacy of the local datasets is the fundamental premise of the federated machine learning. To prevent models from revealing the data, a secure aggregation algorithm has been proposed to aggregate the encrypted local models without the need for decrypting them in the aggregator. However, the participation of a specific local learner can still be disclosed through analyzing the global model. Differentially private federated algorithms have been proposed to provide privacy at local learner level rather than protecting a single data sample. But the problem with these algorithms is that they sacrifice the model performance and require extra computation and a specific number of local learners to participate in the model training. Therefore, efficient federated algorithms that delivers models with high performance as well as privacy protection without adding computational burden are highly desirable. An adversary can influence the local training datasets to manipulate the result of the model by embedding carefully designed samples to data poison the federated learning process. Poisoning resilience defense mechanisms are urgently required, as federated learning in its primary form is susceptible to such adversarial attacks. Some neural network models might unintentionally memorize unique aspects of the training data. This is a problem since in case of an attack there is likelihood of data disclosure, which goes against the premise of federated learning. A curious aggregator, or even a local learner, can perform membership inference attacks against other local learners. Such inference attacks can be parameter inference, input inference, and attribute inference attacks, and can jeopardize the privacy of the local learners. Therefore, vulnerability of federated learnings to these attacks and the corresponding defense mechanism should be investigated as well. One of the essential considerations of federated learning is the convergence of the algorithm under limited communication and computation resources. Furthermore, considerations such as optimum number of local learners to participate in the global updates, grouping of the local learners, and frequency of the local updates and global aggregations that includes trade-off between model performance and resource preservation are application dependent and worth investigation. Approaches that sparsify and compress the model parameters are computationally efficient and reduce the resource consumptions are needed to be able to implement the model on low-power devices, such as IoT nodes. Challenges and considerations in wireless settings. Owing to the limited capacity of wireless channels, communication bandwidth, noise, and interference has to be considered. This also limits the convergence time, since in this case, convergence times includes not only the computation time on the local learners and the aggregator, but also the communication time within them, which depends on the wireless channel quality. There are model compression techniques and sparse training approaches to reduce the complexity of the model and scale down the model parameters, which in federated deep learning for wireless application, communication cost and quality of the wireless channels should be also considered in the model optimization. Quality of the wireless channel between the global aggregator and the specific local learner will also impact its selections for training and should be considered jointly with other factors.
The authors of the paper did a a simulation of federated learning for one of the applications we mentioned earlier, which was edge computing and caching. Essentially, the simulations that they did was about predicting content popularity in a cache-enabled network for AR applications. And the main idea for this model was that AR users will hold their device camera on a target place like a museum, restaurant, or a park to get more information about. But this selection of the popular content that the model would recommend to the users will be based on the search history of the users and their interaction with the content. Uh, the thing is, unfortunately, this information is normally private and cannot be shared through the network without infringing the privacy of the users. So in this case, this is a perfect candidate to use federated learning so that this service can preserve the user privacy and at the same time be improved. Uh, the results are compared between a centralized model where all the data is available, which will not be the case in a real world scenario, and the federated model. These results are compared also between the number of users that were participating in the training with a root mean squared error as the metric. And as we can observe from the graph, the federated learning model performs almost as well as the centralized model, making it a perfect candidate for this application. So with federated learning in this case, you can leverage the user's data to build a better model without infringing on their privacy. So we did a simple simulation for federated learning, which involved classifying images or like classifying the digits of the classic MNIST dataset. But there are some caveats that we need to further explore. First of all, we used uh, the TensorFlow federated learning package to help us do this task easier. As we can see, this package includes an MNIST dataset, which is perfect for doing federated learning because each of the digits are divided for each client, let's say, or each user. And also each user has a somewhat of a unique writing style for its numbers. Also, since we know that federated data is normally not independent and randomly distributed, this also means that some clients may have more data than others and different amount of data per label. So here, first we can observe like uh, this would be the a sample data of one of the users. So this will be the writing style of one of the users. And here we can observe how the data distribution is divided between different clients. So we can see that, for example, client 2 has much less data on many labels, and the distribution per label for each of the clients is different. And finally, uh, for exploring the dataset, we did a mean image of each of the clients to show how the handwritings are somewhat different. So we can see this is the first client, client 0, client 1, client 2, client 3, and client 4. We can see that the writing styles are different. And in this case, the client 2 may have some noisy data or mislabeled data, uh, or maybe like his or her handwriting is really awful. Then we build a model, which I won't explain very deeply because I think goes a little bit beyond the scope of this presentation, but we just reshape the data so that it can be fed into the model, and we created a simple neural network to 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 fit this data. And for some of the metrics we used, we the loss we defined it, but by the sparse categorical cross entropy, and our metric that we said was the sparse categorical accuracy. Okay, so here is when we start building the federated average process, which the with the model we created before. And as we can see, there are two optimizers, which are the client and the server optimizer, which mainly we use to define different learning rates for the users and for the servers. And this part is really important too because it's how we divided the dataset on each training round to simulate the federated training uh, better. So normally in a federated scenario, there's like a very large number of user devices, but there's only like a fraction of them that are available for training at a given point of time. So the thing we did was, okay, we have the maximum number of clients that would train on each round would be 20. And for each of the rounds, we we grab we grab a random number from 1 to 20 in this case, and then we created a from the from our data set we chose a random sample of that data set using the amount of clients that will be trained. So on each round, this will mean that on each round, uh, there will be a different number of clients training and a different sample of clients training. So this would simulate the federate scenario much better because that's how it usually work on real world production. And just as we can see here next that we created before for our predicted averaging process, this next function essentially represents like a whole round of federated learning, which or the whole decentralized computation. So it consists of first pushing the server state to the clients, then a non-device training for each client with their local data, and followed by collecting and averaging those model updates done on each client, and finally using these updates to produce a new updated model of the server. So here we can see we did this for 100 rounds. We can see how the loss decreases and the sparse categorical accuracy normally increases. So this is a good sign that the model is converging. And then essentially we did the same thing, but we showed it on a more pretty version with TensorBoard. So that we can see the loss, how it is decreasing over the number of rounds. And our accuracy is also increasing over the number of rounds. And also we can see that the number of example changes for every round and the number of batches also. So it's pretty random, like how a normal federated scenario would be.
Concluding remarks. Federated machine learning is an emerging decentralized learning solution that tries to address the energy, bandwidth, delay, and data privacy concerns in wireless communication by performing decentralizing model training. Simulations have been carried out to demonstrate the applicability of federated learning to content popularity prediction in a cache-enabled network for AR applications. Federated learning could approach the performance of the centralized scheme in which the training is performed centrally. Numerous issues and open challenges were also discussed that require further research effort in this direction.